back to Science Fantastic with Professor Michio Kaku. We're going to talk about one of the greatest mysteries in the universe, and these are black holes. In fact, today we're going to be talking about an exciting new book that's just coming out. It's called Einstein's Monsters, The Life and Times of Black Holes by Professor Chris Impey. He's a professor of astronomy at the University of Arizona in Tucson. And he's the author of many great books, including Beyond, How It Began, and How It Ends. So in this hour, we're going to talk about black holes, given the fact that scientists, for the first time in history, have been able to photograph up close, photograph at least the event horizon which surrounds the black hole at the center of the Milky Way galaxy. Well, once again, in this hour, we're going to talk about one of the most bizarre, strangest objects in the universe, objects which actually exist. And as I mentioned, a photograph of the event horizon surrounding a black hole is now available. Complements of radio telescope technology. The book is called Einstein's Monsters, The Life and Times of Black Holes by astronomer Chris Impey. So, Chris, glad that you could once again be on Science Fantastic.
Yeah, it's a pleasure to be with you.
Okay, well, once again, when you were a youth, what steered you in the direction of astronomy and science, and how did you get interested in black holes?
Well, I've been in the States for a long time, but I grew up in the UK, and as you know, we don't have very good starry skies there. So I got in, physics is the gateway drug for astronomy, so I was a physics student, and I was actually looking at high-energy physics. The world was very small. But there were some new telescopes the Brits were building in Hawaii and Australia, and so I started getting interested in that. And astronomy was kind of in a buccaneering phase where there were a lot of new discoveries and not huge research teams, so it seemed like a nimble kind of science. And so that was my pathway in. And as far as black holes go, I started getting interested in the huge black holes that sit at the center of galaxies, which when they're active can be the brightest objects in the universe. So my thesis and then beyond was on active galaxies.
Okay, well, let's just get right into the beginning of your book, which talks about the history of black holes. And there was something called dark stars even before the idea of black holes were introduced, going all the way back to the time right after Isaac Newton proposed his theory of gravity. So tell us a little bit about John Mitchell and how he was able to predict this bizarre object called the dark star, which we now call black holes. How did he do that?
Yeah, it was pretty audacious because this is over 200 years ago and well before general relativity. So it's not a formally correct way of talking about black holes. He was extrapolating from Newton's theory, but he was a clergyman. He was an amateur scientist because there really weren't professional scientists back then, and he just had these great ideas and thought, well, if you extrapolate the situation of more massive objects and the escape velocity rises with the mass, you can imagine an object that's either massive or dense enough that the escape velocity is the speed of light, and then nothing should get out, and so it should be a dark star. He didn't imagine the star being super dense. He imagined it just being super large and massive, so he was not correct in that aspect, but just the idea of a dark star goes back all those 200 years.
Okay, but back then, of course, they didn't know what the speed of light was. How could they measure the speed of light using technology that's 200 years old? So back then, I guess, the first estimates of the parameters of a dark star were off, right?
Yeah, it was crude. It was pretty rough. I think the most accurate measurement of the speed of light was done by Fizeau, and there were these very clever timing measurements using Jupiter's moons on the far and near side of seeing what the extra path or time it took for light to travel between Jupiter's moons. So there was a rough estimate, accurate to maybe 10%. And that's good enough to talk about how massive a star would actually have to be for its escape velocity to be that large.
Okay, now in 1915, Einstein proposes his masterpiece, the general theory of relativity, where gravity is a byproduct of the curvature of space and time. And a year later, in 1916, Karl Schwarzschild finds a solution, an exact solution of Einstein's equations. But Einstein, even though he liked the idea of a solution of his equations, he didn't like the idea of what was at the center of the Schwarzschild solution. So could you elaborate for us, what was Einstein's reaction when it was pointed out to him that at the center of his theory there could be something like a black hole?
Yeah, he was kind of perplexed, and he really found it abhorrent. He thought it was a problem of the theory, and in fact it is. The singularity, the infinite cusp of density at the center of a black hole is a problem for the theory. Much later, Stephen Hawking said that black holes contain the seeds of their own demise because they have a singularity. So he just thought it was an artifact of his theory. He didn't really think these would be physical objects that would exist or we could find. And he also didn't really explore the implications of black holes like gravitational lensing and so on. It was left to others to do that back in the 1920s and 1930s.
Now, as I understand, Einstein even wrote a paper showing that if matter swirls around in a star and slowly begins to coalesce into a black hole, it never reaches that point. It never gets small enough, and so he thought that on physics grounds, black holes were an impossibility. But I guess there was a loophole, right? A loophole in the idea that swirling gas alone can create a black hole.
Yeah, there was a loophole, and I think that the real progress, took a while. It wasn't until the 30s and 40s that the people like Oppenheimer and Beta, who were really working on superdense forms of matter out of applications to the atomic bomb, were actually able to do calculations of what, the formation of a black hole would entail. Yeah, Einstein couldn't do those calculations. And you talked about Schwarzschild solution, and people outside the field forget just how brutally difficult general relativity is. There have only ever been a handful of exact solutions to general relativity in these kind of situations, and that's in a century of work.
Okay, and speaking about the atomic bomb, Oppenheimer, the father of the atomic bomb, comes up with the idea of implosion, an idea that Einstein missed. So could you explain to us what this idea of implosion is that gets around the no-go theorem that Einstein had?
Right. So by the 1930s and 40s, with Eddington and others, there's a pretty robust theory of how stars work and how they evolve. And so Oppenheimer was just following the logic of what happens when all the pressure support is lost from a star, when the fusion ends.
And once again, our special guest today is astronomer Chris MP. The book is called Einstein's Monsters, The Life and Times of Black Holes. So stay tuned as we continue a discussion of the most mysterious object in the universe, Einstein's Monsters. Stay tuned. Welcome back to Science Fantastic with Professor Michio Kaku. Our special guest today is Professor of Astronomy, Chris MP, of the University of Arizona at Tucson, and his latest book is called Einstein's Monsters, The Life and Times of Black Holes. And we should also point out that he's written a number of great books, including Beyond, How It Began, and How It Ends. Well, when we last left off, we were talking about the fact that Einstein himself couldn't get himself to believe that these black holes could exist. They were so fantastic. And then here comes J. Robert Oppenheimer, father of the atomic bomb, who invents a new mechanism by which a star could actually degenerate into a black hole via an implosion. So explain to us this new idea of an implosion.
So what's happening in a massive star, this can only happen to a star that's several times more massive than the sun, is that at the end of a star's life, the star is only kept at its size by the pressure from fusion reactions in the core. But when that energy source is lost and there's no more nuclear fuel, then gravity wins, and gravity will force a sort of essentially a free fall collapse, a very dramatic implosion And then the calculations really were only possible in the 1930s and 40s, and Oppenheimer did them, and showed that, logically you would end up with a state that formally met the definition of a black hole. And so at that point, the onus was on people to go out and try and find them.
Okay, so the idea of an implosion was a novel concept, and that was in the 1930s. And I understand in the 1940s, of course, we had World War II, and we were fighting the Nazis. And he came up with the idea of an imploding sphere of plutonium. And that, of course, is the driving mechanism behind the Nagasaki bomb. So, in some sense, the idea of implosion that he originated in the 30s became the seed of the implosion mechanism for the Nagasaki bomb, right?
Absolutely. And it just goes to show how, physics, novel physics or excellent physics, often has multiple applications. You can't always tell how these ideas are going to play out.
Okay, now let's talk about the dynamics of a black hole. Of course, many people want to know the answer to a simple question. What happens when you fall in? So slowly walk through the process by which what happens if your rocket ship slowly begins to orbit around the black hole. What do you see? What happens as you get closer? Many people have seen the movie Interstellar, and Kip Thorne, Nobel Prize winner, was one of the advisors to that movie Interstellar. So tell us what happens as you, heaven forbid, get closer to a black hole.
The best way to sort of think about it is if you and a companion go to a black hole in identical spaceships and your companion stays outside, or maybe you stay outside and watch your companion fall in. Say you stay safely outside, you watching your companion fall in, you'll see his clock move slower and slower, and actually it will asymptotically slow down as it reaches the event horizon. The bizarre calculation in the relativity theory that says that time slows down in stronger gravity fields, and at the event horizon, time slows down infinitely. So to your perspective, that your companion would never actually reach the event horizon. Also, their light would be redshifted by the gravitational redshift, and so they would, gradually change color, and their waves would be stretched out eventually to radio waves. However, from their perspective, they just fall right in on a ballistic trajectory through the event horizon. So there's an interesting difference in perspective from the 2 points of view. And then as to what happens to you, it's the well-known implication that you're spaghettified, which is probably a very unpleasant way to go, because it's not like Stretch Armstrong, just a sort of toy doll being pulled at the feet and the head. This is, you're being stretched out at the level of muscle fibers, bones, and individual molecules. Probably very excruciating, and for sure you will not survive that.
Okay, well, the moon, of course, exerts gravitational force on the Earth, causing the Earth to be stretched a bit, and that gives us the tides. So are you saying, therefore, that as you get closer and closer to the black hole, the very same thing that causes the tides on the Earth basically rips your body apart and you look like a noodle?
That's right. So the difference in the gravity between your head and your feet, or even if you're on your side, between one side of your body and the other, is going to be enough to disrupt the matter, the material of your body. However, when you do the calculation and scale it up, because we know now there are big black holes in the universe as well as dead star-sized black holes, there's some level of around 1,000, maybe a few thousand times the mass of the sun, where although the gravity of that black hole, the total gravity, is of course much more because it's a bigger black hole, the stretching force is actually less. And so that's the boundary at which you might be able to survive falling in. So if you want to do the experiment, if anyone ever gets to do it, then you got to find a big black hole, and you could survive falling in.
Now, as you get closer to the event horizon, the point of no return, ancient light that has been orbiting around the black hole for millions of years, you start to encounter that. So what happens? Is it possible that you can see the past, see the origin of where the black hole came from, because you're now looking at light that's been trapped by the black hole for eons? What are your thoughts?
That's right. There's a place that's formally twice the distance of the event horizon from the singularity, at which light will just orbit, go around in circles. And so, yes, light that ends up in that situation could be very old light. And so, yes, you could be witnessing that light. There's another piece of this story, which is that the information that essentially falls into the black hole and is lost forever, including the radiation, there's arguments as to whether there's somehow that is preserved on the event horizon. This is the holographic theory of black holes, which doesn't have any direct experimental support, but it's an intriguing idea. And that sort of argues that the information that seems to be lost in a black hole may not be totally lost, because it may essentially be coded on the event horizon somehow. So as you fell into the event horizon, you might see the history of that radiation falling in too.
Now, we'll talk about that, but when you fall into a black hole, you don't come back out again. So it's like the ultimate Roach Motel. Everything checks in, nothing checks out. However, that seems to violate the quantum theory, because in the quantum theory, well, things are reversible. Information is never lost. So here's the question. If you take the Encyclopedia Britannica and you throw it through the event horizon, the point of no return, is the information of the Encyclopedia Britannica lost forever, or does it come back somehow? And I understand that Stephen Hawking himself made a mistake, and he admitted it. Could you tell us about that?
Yeah, the implication, the simple implication of the black hole theory is that the information is lost, and so formally one way of expressing that is to say that black holes have large entropy or disorder. So a black hole that's the mass of the sun has 100 million times more entropy or disorder than the sun itself, which is a reflection sort of all the myriad ways that matter could end up in a black hole, and you can't distinguish between them. The black hole is mute to all the histories of matter that went into it. So the question of whether that is ever retrievable or could be retrievable is an active research question. I think it's still an active research question, because the issue you allude to, the inconsistency between information lost in the black hole and the theories of quantum physics is not really fully resolved. There are some very interesting ideas out there, but it's an active field. I think several hundred research papers a year are still being written on that topic.
Okay, well, Stephen Hawking was famous for saying that black holes are not really black. Blackness means you absorb everything, including light, and nothing ever escapes. But then Hawking came up with something called Hawking radiation, which really was quite a new discovery, the interaction of the quantum theory with general relativity. Stay tuned. Back to Science Fantastic with Professor Michio Kaku. Once again, our special guest today is Professor Chris MP, author of a new book, Einstein's Monsters, The Life and Times of Black Holes. Well, of course, many people know the name of the late physicist Stephen Hawking, but what was his main contribution? The fact that, well, black holes are not really black. Things are black because they absorb light, so a black hole should be the ultimate Roach Motel. Everything checks in, nothing checks out. But here comes Hawking, who says that, well, that violates quantum mechanics. Quantum mechanics says that, well, you can never have perfect blackness. Perfect blackness violates the Heisenberg uncertainty principle. Therefore, he said, there should be grayness coming out, or radiation. So tell us a little bit about what is Hawking radiation. Have we seen it, or is it much too faint to pick up with our instruments?
Yeah, it's extremely challenging. I mean, Hawking was himself hoping that it might be detectable, because he thought there was a Nobel Prize sitting there, which really only happens for a discovery rather than a theory. So Hawking radiation being seen would have almost certainly netted him a Nobel Prize. He knew that in physics, in the vacuum of nature, particles and antiparticles come in and out of existence all the time. That's well established. physics, microscopic physics. We've seen it happening in the lab. And in his view, his insight was that if this process happens near the event horizon of a black hole, there's a finite probability that one member of the virtual pair will go inside the event horizon and the other will come out. If it's an antiparticle, then it'll annihilate immediately with the particle and lead to a photon. So the net effect of this phenomenon occurring near the event horizon is a very small loss of mass or equivalently energy. And he put a calculation on the temperature, and it's an amazingly small number. It's like a billionth of a Kelvin. So there's no conceivable way astronomers can measure the temperature of a black hole at that level, especially since they're usually surrounded by gas and it's very hot and messy. So unfortunately, that very low temperature of Hawking radiation is unobservable. But the implication that black holes have a temperature and they radiate energy and equivalently they evaporate, slowly lose mass, is very profound because it changes our view of black holes completely.
Okay, now let's go to the experimental side of things a bit. And as I mentioned, we have radio astronomers who have lashed together the radiation they pick up from outer space, and they've been able to get a picture of, well, not the black hole itself, but the event horizon surrounding the black hole. So tell us, how do you do it? How do you get all these radio telescopes, lash them together to get an effective radio telescope the size of the Earth? How do you do that?
Yeah, it's a great experiment, and I'm pleased that one of the collaborators in this research group is in my university, my department, and we have one of the telescopes is in Arizona, so I'm pretty familiar with the project. So the key to imaging or resolving the event horizon is you need incredible angular resolution. You need to make a much sharper image than is possible with most optical telescopes. Also, the center of our galaxy is completely opaque to visible light. I think 1 in a trillion photons reaches us from the center of our galaxy. So you can't possibly do this experiment with optical light or even infrared. So you move out in wavelengths to radio waves or millimeter waves, much longer waves, to make the galaxy as transparent to them so the radiation can get out, 26,000 light years. And then to get that sharp resolution, a single radio telescope just won't do it. It'll make a very fuzzy radio image. So you essentially mimic a super large telescope.
Okay, Chris, we have to take another short commercial break, but afterwards we're going to continue a discussion of your book, Einstein's Monsters, The Life and Times of Black Holes. Stay tuned. Continue a discussion of the greatest mysteries in the universe. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, we're talking about one of the strangest objects in the universe. It's a subject of science fiction, but they exist, and we now have a photograph of such a monster. So when we left off, we were talking about the experimental domain now of how you actually see these things in outer space. Some people wonder, well, if it's black, how can you possibly see something that's invisible? So tell us a bit about that. I mean, given the fact that black holes are black for the most part, they absorb radiation, how can you possibly detect them from the Earth?
So what you're seeing and what they've seen with this radio telescope array is the event horizon silhouetted against hot glowing gas behind it. So it's sort of backlit, if you like, because black holes in dense regions of space are usually surrounded by swirling gas, accretion disks, and that gas glows. This radio telescope array has the sharpness, the resolution to make an image of the event horizon, and it will be backlit by this hot gas. And they need a radio telescope basically the size of the Earth. Now, we can't cover the Earth with radio antennae, but you can take different radio antennas across different continents and coherently combine their radio waves to synthesize, it's called aperture synthesis, a telescope that acts like it's the size of the Earth in terms of the sharpness of its radio images. That's a very challenging thing to do, but this team has done it.
And given the fact that we've been able to do this now, what are the next steps? Are we going to be able to peer into the center of other galaxies and have maybe an encyclopedia of different kinds of black holes, or is this just one of a kind? And what about black holes that are stellar inside our own Milky Way galaxy? Well, one day we'll be able to see them as well?
You know, the ironic thing is that this big black hole, 4 million times the mass of the sun and 26,000 light years away, is easier to do this experiment on than the smaller stellar black holes much nearer to the Earth. And the reason is that the size of the event horizon goes up with the mass of the black hole. And so this big black hole in the center of our galaxy is tens of thousands of times more massive than a stellar black hole. So its event horizon is tens of thousands times bigger. But it's only a few hundred times further away than the nearest black holes, which are a few hundred light years. So ironically, it's easier to make an image of this event horizon than of any of the stellar mass black holes that are much closer than a few hundred light years of the Earth. And actually, it's not going to be possible to do this with those black holes. So it's a bit of a one-off. And so very exciting to see what happens, because we're not going to get other chances to do this experiment. And then if you go to other galaxies where the black holes are bigger still, they're again much further away. They're millions of light years away rather than a few tens of thousands. So they're hundreds of times further away, and they're also impossible to image. So this really is almost a unique experiment at the moment.
And there's another instrument called LIGO, a gigantic instrument, 2 of them in fact, and they've been able to pick up gravity waves from colliding black holes. So tell us a little bit about LIGO, which eventually won the Nobel Prize for the people that perfected the experiment.
Yeah, this is very exciting science of the last few years. Their first detection was in late 2015, published the following year, and now they've had 6 or 7, I think, other black hole mergers. So it's an exquisitely precise physics experiment, the most precise physics experiment ever done. And what they're looking for, again, a prediction from general relativity, is that when you have a binary star system where both of the members are massive enough to die as black holes, and those black holes eventually spiral together and merge, they will release a torrent of space-time ripples, or gravitational waves, that travel out at the speed of light and eventually reach the Earth. They're extremely tiny perturbations or ripples in space-time, so very, very difficult to detect. Many people thought this experiment was impossible, and very deserving of a Nobel Prize in the fact that they succeeded a few years ago.
And with LIGO, one day people will put them in outer space perhaps, right? And even get baby pictures of the infant universe. So we're talking about a whole new era of astronomy opening up. Welcome back to Science Fantastic with Professor Michio Kaku. With us today is Chris MP, author of the book Einstein's Monsters, The Life and Times of Black Holes. And this is a great time to be an astronomer because we have instruments like LIGO, which gave us indications that gravity waves are not science fiction, but we've actually been able to measure gravity waves from colliding black holes. And then we have the Event Horizon Telescope, capable of actually photographing the event horizon surrounding a black hole. So it's a great time to be an astronomer. By the way, let me ask you a question. Have you seen the movie Interstellar? Do you think it was accurate? And, of course, they go through the event horizon. That's something that maybe you shouldn't do. But tell us a little bit about that, too. What happens when you go through the event horizon? So what do you think of the movie Interstellar with Matthew McConaughey?
I thought it was great. I mean, you know, with science-inspired movies, they're still creative work, so I always cut the movie maker some slack of mostly getting it right. A little artistic license is fine, but that movie, as you know, had Kip Thorne as a scientific advisor. And, you know, that's a pretty good place to start because he's going to make sure it's pretty accurate. In fact, Kip Thorne said that the simulations they did to create the images, the animations, the graphics for the movie actually led him to publish 3 or 4 research papers. So this was an amazing confluence of creativity and movie making with actual research and relativity.
And also, he published a textbook, well, not a textbook, but a picture book about the making of the movie. And the movie ends with Matthew McConaughey hovering in some kind of gigantic, strange cube, which I identified as a hypercube, because the movie ends on string theory. Now, tell us a little bit about what happens if you go through the black hole and enter the world of, well, science fiction. Nobody knows what happens, but there are theories. There are theories as to what might happen, including maybe there's a gateway to another universe, or maybe it just ends right there. So what are your thoughts about speculation, because that's what it is, speculation, about what happens if you fall through the event horizon, like in the movie, and like Matthew McConaughey, wind up in the fifth dimension?
Yeah, I mean, it's fun to speculate, and the theory is incomplete. We have to admit that our theories of gravity are incomplete when it comes to understanding black holes. So it's a fun way to speculate. The business of a black hole being a portal to another region of space-time and coming out as a white hole, it's formally possible, but there's no evidence for that. Our universe is actually rather dull in terms of its space-time. Space-time is essentially flat on all the large scales, and black holes are little pinched-off pieces. So I don't think that happens. However, a spinning black hole turns formally inside a spinning black hole, there will be something called a time-like curve, where if you were there, and this is a big enough black hole that you survived falling in and didn't get stretched apart, you could travel along that timeline curve backwards and forwards in time and sort of meet past and future versions of yourself, I assume. So that would be kind of interesting.
And wasn't it mathematician Roy Curry back around 1963 who took a spinning black hole, found an exact solution of Einstein's equation, and if you fall through the ring of the spinning black hole, it's like going up an elevator. You wind up on a parallel floor of another universe. And if you go through the elevator one more time, you wind up on a second parallel universe. And basically, you hit the up button, you go through the event, you go through the wormhole, and you wind up on many different parallel universes. So what are your thoughts? Of course, this is pure mathematics. It has nothing to do with reality as we know it. But what are your thoughts about whether or not we have to take some of these solutions seriously?
Well, I think we have to take them seriously. That was the monumental achievement that Roy Kerr did, and as we were talking about earlier, solving the equations of general relativity in these situations is incredibly difficult. So there's Schwarzschild, and then there was Kerr in the 60s, and that's almost it. I mean, two exact solutions in the 20th century. And if we take the math seriously, I think it was a famous physicist, maybe Murray Gell-Mann, I don't want to misquote, who said, we trust the mathematics, it's caught us every time. He's talking about physics, manifesting in the real universe, things that we describe mathematically. So if we trust it, then maybe these speculations about other dimensions and other space-times are legitimate. I think we should take them at least semi-seriously.
Now, Stephen Hawking took these solutions, these bizarre solutions, seriously enough that he had a theorem that said that if you have something called negative energy or negative matter, you can stabilize some of these bizarre solutions of Einstein's equations and perhaps even get a wormhole machine or a time machine. And he was able to actually show, mathematically speaking, the limits of how far you can push Einstein's equations so that they would allow time travel or wormhole travel, and, make some statements that can then at some point in the future be testable. But of course, this is not going to happen in our lifetime. We're not going to be able to test any of these solutions. But, well, what are your thoughts? Negative energy, negative matter, we've never seen them. They may not even exist. But if they do exist, wouldn't that force us to rewrite the history of black holes?
Yes, I think so, and that history does need to be rewritten because, we're still faced with the problem you mentioned early on that, the gravity theory that leads us towards the idea of black holes is inconsistent in black holes with quantum theory and the reversibility of microscopic reactions that we see in the lab. And nobody's figured that out yet. It's led to ideas like a firewall that somehow destroys the entanglement that particles might have across the event horizon. There are all sorts of esoteric ideas, but it's an unsolved problem in physics.
Chris, unfortunately, we have run out of time, but thank you so much for being on Science Fantastic.
I've enjoyed it a lot, Michio. Thank you very much.
Great. And once again, our special guest today was astronomer Chris MP of the University of Arizona in Tucson. The book is called Einstein's Monsters, The Life and Times of Black Holes. And he's the author of a number of great books, including Beyond, How It Began, and How It Ends. And you are listening to Science Fantastic.